In our zinc and copper cell, why was zinc oxidized and copper was reduced and not the other way around? In fact, for any redox reaction, what determines which element is oxidized and which is reduced? Good question. Metals, because they have a few valence electrons, uh, like to lose electrons. In other words, they tend to be easily oxidized. But metals differ in how easily they lose electrons. The fact that different substances oxidize more readily than others is the driving force behind electrochemical cells, and it is this force that forces electrons through the external circuit from the anode to the cathode. This force is known as potential difference or electromotive force, and you might see EMF or E. Potential difference is measured in volts and thus is also referred to as the voltage of the cell. Voltage is a measure of the tendency of electrons to flow. The higher the voltage, the greater the tendency for electrons to flow from the anode to the cathode. What we are going to use now is our tables of standard reduction potentials for half reactions, and that's table 8. I'm just going to pause and bring it up. Okay, so I just got into the course. If you go into your data booklet, I want to show you what table I'm talking about. So hopefully you have this printed. It's the very last page, actually. Here we go. Half reactions. This is what I'm talking about here where we're going to look for things, okay? So make sure you have this printed out. If not, you want to press pause and get this table here. What we're going to be starting at is this hydrogen reaction. Look, it goes 0. Everything above it is positive. Everything about it is negative. I want you to notice too, all of these reactions have electrons on the left side. So we're gaining electrons. These are all reductions, okay? So this is the table we're going to use for the notes that we're doing here. Okay. I moved this funny. Oh well. We will use it. Okay, these tables compare the ability of different half reactions to compete for electrons or become reduced. Since half reactions cannot occur on their own, all values are determined by comparing a half reaction to that hydrogen. And here's the reaction. Okay, a couple things you have to know. This little circle there means that there's these standard conditions. It happens at 25 degrees. It happens at a standard pressure and the same concentration. You don't need to know that too much. Okay, in this hydrogen half cell is assigned a voltage of 0. If the half reaction is better at getting electrons, then the half reaction will undergo reduction and hydrogen will be oxidized. The other half reaction will then be assigned a positive voltage. Okay, so if it's above it, it is better at being reduced. Okay, so we're always looking at the one that is the highest. That one is going to stay as it is. The one below it is going to change. So just to give you an idea, this is gold is above tin. So this one would stay as is. The tin would be, we would flip it around. That's what I'm saying there, okay? So it matters where it is on that table. Okay, for example, if we have copper and hydrogen are joined together, we find that copper will gain electrons from the hydrogen half cell. Thus, copper is given a positive. So if you look on your table, copper is found above hydrogen. Am I telling a lie here? Where is copper? Copper, 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 copper. Copper right here is above hydrogen. Excellent. Okay. Hopefully you guys can see my little cursor on your video. Okay. So we take the value from our table, the voltage, which was 0.34. Okay. Since both half reactions cannot undergo reduction, we must reverse the equation that will undergo oxidation. We must reverse the lower on the table. Okay, so we write copper the way we saw it on the table, and we reverse the hydrogen. So we have 0.34, and 0.00. Those are values from the table. Now we add these half reactions together. So we add all of the reactants together and all of the products together. So we have Cu2 plus H2 gas goes to, look, spectators found on both sides. We don't need to write those. Solid copper plus 2H plus aqueous. Okay. We see in that same table that zinc has a negative E, indicating that it's not as good as hydrogen. So if we look on that table, you should be able to find that zinc has a voltage of negative 0.76. So it's lower than hydrogen. So we're going to keep hydrogen the way it was. It's going to be reduced. But zinc we have to flip. And notice whenever we flip it, then we make its voltage the opposite sign. Okay? So if we were to add these two reactions together, we would get a total voltage of 0.76. We could go through the same thing with our spectators and write the full reaction as well. Okay, so how to calculate voltage of electrochemical cells. Looking back on our zinc copper cell, we can use that table to calculate the voltage, but also explain why it's zinc that underwent oxidation. Before calculating the voltage, you must first determine which cell is oxidized, which one is reduced. Find the copper and zinc half reactions in the table. Be careful, there's often more than one half reaction for an element, so just make sure you're always looking at the right one. For copper, we want to locate the copper 2. Okay, so we have copper is 0.3. This is what your table should say. You have copper plus 2 electrons going to Cus, and we get 0.34 volts. And I have zinc aqueous plus 2 electrons goes to zinc solid. And this had a value of negative 0.76. Okay, this is higher up, so it stays as is. This one is reduced, or this one has a bigger value. That's another way you could look at this. This one is reduced, and this is going to be oxidized. So in the table, all reactions are written as reductions. The E value indicates which half reaction is better at competing for electrons. Since copper has a larger value than zinc, copper is reduced, forcing zinc to be oxidized. So we reverse the zinc equation, and in doing so, change the sign for zinc. As long as electrons cancel out, we can then add the equations together to get the full redox and determine the voltage of the cell. Okay, so we keep copper as is. Oops, that should be a line. I'm just copying this right from the table. So if you can't read something, you should just look on the table. Okay, we get 0.34 volts. Now we take zinc and we write it completely reversed. The reactants become the products become the reactants. And this is the important part. Instead of writing negative 0.76, we put positive 0.76 volts. Okay, now we add this reaction together. Our spectators, we have the same amount of electrons on both sides. So we just do all of our reactants. Okay, so I've done everything on the left side of the arrow. Now I take everything on the right side of the arrow. Order doesn't matter that much. That should be an arrow. That does matter. As long as you have the right ingredients on the right side. Okay, my total voltage, I add this up. 0.34 plus 0.76 is 1.10 volts. So if we were to actually make this electrochemical circuit, or cell rather, and you put a voltmeter, you should get a reading of 1.10 volts. When creating an electrochemical cell, always reverse the half reaction that results in a positive value of E when they're added together. So we should always get a positive here. A positive value indicates spontaneous. They always have spontaneous. So we should always get a positive E. So if you do all your work and you get a negative value here, something went wrong. It is not an electrochemical cell. I'm going to stop the video here and I'm going to do the next section in another video.